Welcome to qnawire.
In this question, we have a source of sound that oscillates in a simple harmonic motion with an amplitude of 17 centimeters. A detector is placed along the line of motion of the source, and the source emits a sound of a frequency 800 hertz that travels at a speed of 340 meters per second. If the width of the frequency band detected by the detector is 8 hertz, we are to find the time period of the source. So this is basically setting us up to do a Doppler effect question. We know that the source is going to be moving back and forth, and sometimes it's going to be moving away from the detector, sometimes it's going to be moving towards the detector. The maximum frequencies, the difference between the maximum and minimum frequencies heard is 8 hertz. And we're going to hear the maximum frequency when the source is moving at its quickest towards the detector. And then we're going to hear the minimum frequency when it's moving its quickest away from the detector. So this is clearly a Doppler shift question. Now, one thing that we can do with the Doppler information is find what is the maximum and minimum speed what is the maximum speed towards and away from the detector? And then we can go on to later find what the period is once we have that information. So what I'm going to do is I'm going to set up a Doppler shift equation here. I already have the speed of sound written down. The speed of the observer or the detector, U0, is going to be just 0 meters per second because we weren't told that it was moving at all. The emitted frequency is 800 hertz. And we're trying to find what the US is, the speed of the source. We were also told that the frequency band is 8 hertz. So what that means is the difference between the maximum frequency that's heard and the minimum frequency that's heard is 8 hertz. So I can make a little equation like this. Then I can go ahead and sub in the regular Doppler information, the regular equation. And for the away, I'm going to change the minus to a plus because US is considered to be negative when the source is moving away from the detector. So we can take that into account by changing that to a negative. Okay, let's do some math here. Now we know that V0 is 800, so I'm just going to divide the whole thing by 800. So that's going to give me V over V minus US minus V over V plus US, and that's going to be 8 over 800, so that's going to be 0.01. So I'm just dividing the whole thing by V0, which is 800. Then I'm going to create a common denominator here of V minus US times V plus US. So that's going to give us something like this on the top. And then I'm just going to multiply everything in. So we've got V squared plus V US minus V squared plus V US on the top. Obviously, we can go ahead and cancel out those V's. On the bottom, the middle term is going to cancel out, so we just get V squared minus US squared. So I get 2 VUS on the top, and I'm going to just multiply everything by the bottom. So that's going to be 0.01 V squared minus 0.01 US squared. Now I can sub in the V, that's 340 meters per second at this point, or I could have done it earlier, just a little bit cleaner. So I'm going to do that now, and I'm also going to pull the 2 VUS to the other side. So we have everything equaling 0 here. So it's going to be negative 0.01 US squared minus 680 US squared, and then plus 1156. Now, we can use the quadratic formula to solve this quadratic equation for US. I just went ahead and used my calculator. I got one really big answer and one reasonable answer. So the reasonable answer for US was 1.7 meters per second. Okay, so the maximum speed of this simple harmonic oscillator is 1.7 meters per second. Okay. How does that help us to find the period? Well, we know when a simple harmonic oscillator is going back and forth, we have an exchange of energy from kinetic energy into potential energy. The maximum kinetic energy of the oscillator has to be equal to the maximum potential energy. Right? So we're going to have the maximum kinetic energy in the middle, and then the maximum potential energy once the oscillator has reached its maximum length, or its once it's reached its full amplitude. So we can calculate the KE max because we do have the speed, right? The maximum speed. So that's going to be 1/2 m US squared. And the maximum potential energy of a simple harmonic oscillator is 1/2 kx squared, where x is the amplitude. We know the amplitude is 17 centimeters. So basically what that allows us to do is to solve for m over k, which is exactly what we need for the period. So we're not going to be able to get m or k themselves, just the ratio between them. So I'm going to divide by k, and then I'm going to divide by US squared. So I get m over k is equal to x squared over US squared. And the amplitude was 17 centimeters, so that's 0.17 meters. And then we've got 1.7 for the speed. So once we plug that into a calculator, we get 0.01. So m over k is 0.01. And we can then use that to find the period. So the period of a simple harmonic oscillator is going to be 2 pi times the square root of m over k, which we just found. So once we sub in our m over k and multiply by 2 pi, we get a final answer of 0.628 seconds, or using our sig figs, we only have one sig fig, so that's going to be 0.6 seconds. So the period of this oscillator is 0.6 seconds.